So, good evening. Today we will start with a new topic, chemometric analysis in medical applications. I will be out of station for this week from tomorrow onwards. So I thought not to start the new topic related to the mathematics, the convolution part. So we'll be discussing about this chemometric analysis today, and after my return in the next week, we'll be continuing with this convolution and the other parts of the DSP. Okay. So what is meant by chemometric analysis? Okay. Over here, uh, the chemometric word, it is the word which is a new term you must be learning or hearing for the first time, right? So what do you mean by chemometric, right? So chemo, it comes from the word chemical. Okay. Metric means it is a mathematical or the statistical parameter that is used to quantify or to get some qualitative information about any substance. Okay. So when you combine these two, so what we say is that to have an understanding of a sample, if we do some analysis, then it is and that analysis, it gives us some information about the chemical structure, then it is regarded as the chemometric analysis. Okay. So why we are studying this in today's class in biomedical application? This is because the chemometric analysis, it has become an integral part of digital signal processing nowadays. Okay. Due to the what you call due to the advent of the due to the advent of the advancement in the field of this machine learning and artificial intelligence, now people are combining the chemical methods with the machine learning methods or the other uh, this statistical method to gain an insight about the chemical information of a substance. Okay. And these can be very useful in understanding or promoting the yeah, healthcare benefits. Okay. Now when we talk about the chemical analysis, the spectroscopic analysis, it is one of the most widely used method. Okay. What do you mean by spectroscopic analysis? In the spectroscopic analysis, what happens is that you have a matter. Okay. Now you can make an electromagnetic radiation incident onto this matter, then either this electromagnetic radiation, it will pass through the object, and on the other side, whatever the transmitted EMRs are there, you analyze that. Or if it is not transmitting, then what happens? It may be reflecting. Okay. Now in either of these case, when the EMR is passing through the object or it is being reflected, some amount of energy is imparted into the matter. Okay. Now, how much amount of electromagnetic radiations have been absorbed by the matter? It gives us information about the chemical structure or the electronic structure within the molecules or the substance. Okay. So, what are EMRs, electromagnetic radiations? These are nothing but synchronized oscillations of electric and magnetic fields. Okay. So, it looks something like that, and all of you must have studied about this one. Now, what are the different electromagnetic radiations that are being used? The most commonly used electromagnetic radiations that are used in various spectroscopic techniques are radio waves. Okay. So where the radio waves are being used? Any idea? Any spectroscopic technique where the radio waves are being used? True. So, in NMR, nuclear magnetic resonance spectroscopy, or in many cases it is regarded as MR spectroscopy, magnetic resonance spectroscopy. Over there, the radio waves are being used. Okay. Then microwaves. What about the microwaves? Similar to NMR, there is another spectroscopy which is regarded as ESR, electron spin resonance, or EPR spectroscopy. Electron spin resonance or electron uh, paramagnetic resonance spectroscopy. Okay, ESR or EPR, in ESR or EPR spectroscopy, the microwaves they are being used. Okay, then coming to the infrared spectroscopy, usually in infrared spectroscopy there are in the infrared region basically there are three regions: near IR, mid IR, and far IR. Three regions are there. However, for the spectroscopic applications, near IR, NIR, or mid IR electromagnetic radiations, they are being used. When we use NIR, then the spectroscopy is regarded as near infrared spectroscopy. On the other hand, when we use mid IR electromagnetic radiations, then they are regarded as normal FTIR spectroscopy or IR spectroscopy. Okay, so then we have the visible light. So when we have this visible light, then it is called visible spectroscopy. Okay, which is very commonly found in many of the laboratories. Similarly, ultraviolet spectroscopy, it is there when we use the ultraviolet spectroscopic technique. Usually, in most of the equipments, in most of the labs, basically, you will find UV vis spectroscopy, UV visible spectroscopy. So, in a single spectroscope, you will be having both UV source and the visible source, and it will generate initially the UV radiations will be generated, and then the visible range will be generated to analyze the samples. Okay, so we have this UV visible spectroscopic technique. Then comes X-rays. Where do we use X-ray? XRD is one of the techniques. Then any other techniques? Any other technique? X-ray fluorescence spectroscopy. Okay, X-ray fluorescence spectroscopy. Okay. Then we have the gamma rays, gamma spectroscopic techniques. They are also there. Now, when we talked about this spectroscopic technique few moments back, what I told you that these EMRs, they may have energy in the form of momentum or angular momentum. Okay, so they are being imparted into the matter. So these energy packets, they are being imparted into the matter when these EMRs interact with the substance. Okay, the substance may be a molecule, it may be a large sample. Okay, so it may be an atomic molecule. So the EMRs imparts energy to the sample under the test. Okay, now this property, how they are interacting, how these electromagnetic radiations they are interacting, it is being explored in the field of spectroscopy. Okay, it is being explored in the field of spectroscopy. Now coming to the electromagnetic spectrum. Now if you look into the electromagnetic spectrum, we have these radio waves towards our extreme left, and as we move towards our right, we get to the gamma rays. So what is happening? If you look over here, radio waves, they are having the longest wavelength, and as we go towards the gamma rays, they are having the very small wavelengths. In other words, it is having a very high frequency, or you can say as the frequency increases, there is an increase in the energy content of the electromagnetic radiations. So in other words, you can say that as we move from left to right, there is an increase in the energy content of the radiations. Okay. Now, since there is an increase in the energy content of the radiations, so higher the energy, thus it is capable of analyzing the more and more smaller say samples. Okay, say for example over here when we talk about the gamma rays, it is having the highest energy over here, so it can give you information to analyze the subatomic particles. Okay, to analyze the subatomic particles. Okay, when you use x-rays, x-rays can give you information about the atoms. When we are using the ultraviolet radiations, it can give us information about the molecules at the molecular level. Okay, then if you are using visible light, it can give you information about the micron size particles, and so on as you go on the other side. In radio waves, as I told, radio waves are not directly being used, it is just used to change the energy state of the precessing protons, okay, which are being generated due to the placement of the samples in a high magnetic field. Okay, so which we call as the precision frequency omega naught equals to gamma b0, where gamma is the gyromagnetic ratio. Okay, gyromagnetic ratio. So what is this omega 0? In NMR, what happens is that you have a very high magnetic field, and within this magnetic field you apply or you place the sample. Okay, now when you place the sample over here, so what happens in the presence of this high magnetic field, all the protons in some of the atoms, one of the common NMR technique is H1 NMR. Okay, so in H1 NMR, the hydrogen protons which are abundantly present in most of the biological samples, these protons, they start to vibrate, no, precess. What is precess? All of you must have played with the top lattu, right? So when you uh, throw it onto the ground, what it does, we expect that it will be rotating on its axis in a straight manner, but it does not work in that way. Many a times you will find when it is moving, it is forming an elliptical path. Okay, so when it is not rotating on its original what you call axis, and it forms an elliptical path, then this movement it is called precession. And when it is moving, it is having a frequency. Now that frequency it is regarded as precession. Okay, that frequency it is regarded as frequency, and that frequency it is dependent on gamma b0. Okay, so this equation it is regarded as, or this frequency it is regarded as Larmor frequency. Okay, now what happens, these are there, but what happens in a molecule, you also have electrons. So the electrons, they form an opposite magnetic field, they form an opposite magnetic field. So what they will try to do, the proton will try to be it's on its standing on its leg, but there is an opposite force. तो क्या होगा? So if you look into the net magnetization vector, it should be at the it should be parallel to the net magnetic field. Okay, but it would due to the presence of the magnetic field, due to the electrons, it will not be exactly parallel. The net magnetization vector it would be slightly tilted. So you have to bring this to this position, to the high energy level, highest energy level. Okay. So what you do in that case, you have to apply the radio waves, RF pulses. When you give the RF pulses, what will happen? The net magnetization vector will be getting parallel to the B0. Okay, it will be getting parallel to the B0. Now again, when you remove the thing, it will come down to its original position. Okay, it will come down to its original position, and when it is coming down to its original position, it was having an, it went to the highest energy state by absorbing some energy. So while it is coming back to the low energy state again, what will happen? It will release that energy. So it absorbed radio frequency. What it will emit? Again the radio frequency. So the radio frequencies or the radio waves, they will be emitted, and those radio waves are being captured and analyzed in NMR spectroscopy. So I am not going into the details of this one. Similarly, when you talk about this ESS spectroscopy, it is also following the similar pattern. However, what happens in ESS spectroscopy, we are studying the electron, the magnetic field generated by the electrons, and the interference comes from the proton. Okay, just like a married couple, husband ka interference will be with wife, wife ka interference will be with the wife, right? Husband wife, wife husband, this interrelationship will be happening. So atoms, when you talk about the atoms, the protons and the electrons, they are forming a couple, and because of that you are getting the stability. So iska interference iske liye rahega, proton will be having interference from the electrons, electrons will be having interference from the protons. Okay, और बेचारा न्यूट्रॉन पिस जाता है. Okay. So anyway, so over here what happens is that when we talk about this electron spin resonance, instead of the radio waves, we use the microwaves in electron spin resonance. Okay, so this process where the magnetic field of the electrons, it is affecting the net magnetization vector of the protons, it is called electron shielding effect. Electron shielding effect. Electron is shielding the proton from the external magnetic field. Okay, electron is shielding the proton from the external magnetic field. Okay, so this is the thing. The same thing happened over there, proton shielding effect. Proton will save the electrons from the external magnetic field. Okay. So coming to the infrared and all these things, I will go to the next slide. Over there you will be able to understand what is happening. So this is called the energy level diagram. Okay. So you must have heard that there are two states. So one is the ground state, okay, which is regarded as the E0, which is regarded as the E0 ground state. When you give some energy to the electrons present in the ground state, it goes to the E1 state, which is an excited energy state. Okay. So what is happening? The electrons are moving from the ground state to an excited state. So electrons are moving, so it is called electronic transitions. So it is called electronic transition. Okay. Then again from there it comes back. So this is called absorption emission spectroscopy. Okay, and it happens in visible and the UV spectroscopic techniques. UV and visible spectroscopic techniques, you will be having this what you call electron absorption and emission thing happening. On the other hand, you will see within these ground levels, there are some big lines which are regarded as V0, V1, V2, V3. These are called vibrational energy. These are called vibrational energy. And again, within these vibrational energy levels, if you see R1, R2, R3, R4, so these are called rotational levels. Okay. So within the ground state, there would be vibrational energy levels, there would be rotational energy levels. Okay. So what happens? The molecules that vibrates, when you excite them with the electromagnetic radiations, they show the vibrational energy transition. So it may go from V0 to V1 or V1 to V2 or V0 to V2, whatever the possible combinations are there. Okay. Similarly, if if you see in the electronic transitions, if you see the transition, it is quite high. So the energy required is quite high. Okay. In vibrational energy, the energy requirement is lower than the electronic transition state. Okay. Then comes our rotational energy levels. In the rotational energy levels, what happens? The energy transition is much lower than the vibrational levels, because if you see, the distance is quite smaller. Okay. So in rotational energy levels, you will be having the requirement of quite low energy content. Okay. So this is the spectral diagram of a xenon lamp, which is usually used in both visible light and near IR spectroscopic technique. Okay. So now coming to the chemometric analysis, so there are, how do you select the spectroscopic method? In the first one, we have this UV visible spectroscopic technique. As I told you, there would be electronic transitions and there would be absorption emission phenomena. Okay, absorption of the electromagnetic radiation, that means UV and visible electromagnetic radiations by the electrons. So it will absorb, go to the high stage, and it will come down by emitting the excess energy. Okay. Then in the absorption spectroscopy, we basically have two types of spectroscopic techniques which are regarded as the NIRS, that means near infrared spectroscopy, and IR spectroscopy. Over here we have this vibrational and the rotational modes of energy transition. Okay. Over here we are having vibrational and rotational modes of this energy transition. Okay. Now next we are having Raman spectroscopy, which has been named by the Indian scientist Dr. C.V. Raman sir. So in his name this Raman spectroscopy is there. So what happens is that what he said, that all these things is happening, that's quite fine, but what happens, some radiations, they are being scattered from those energy levels. Okay, whatever we have discussed. So Raman spectroscopy is all about scattering of the electromagnetic radiations by the vibro-rotational energy levels, and that is being analyzed. Okay. Yeah, and if you look into the wavelength range in NIRS, I forgot to mention that in NIRS it is 800 to 2500. In IR it is 2500 to 50,000 nanometer. In scattering it is 2500 to 2 lakh nanometer. And lastly, this NMR, we already discussed about this one. We are this NMR spectroscopy. If you see, this is the direction of the B0, and our magnetic field of the proton, it is moving at an angle theta, and due to that this elliptical path has been formed, and hence it is regarded as the precision. Okay. Now coming to the spectroscopic techniques. So in the spectroscopic techniques, we already discussed about these things. So you can just go through this if you want. So what happens in chemometric analysis and what are its applications? So herein, if you see the spectroscopic technique ACRS has been given. Surface enhanced Raman spectroscopy ACRS it has been given. Okay. Now this ACRS, what happens? If you see these radiations are there, and from this ACRS we get some signals. Okay, the spectroscopic signals, right? Now these signals, if you see, this is a signal, and underlying within these what you call the signal, whatever you get, there are some hidden signals. Okay, there are some hidden signals. Okay, by applying artificial intelligence, it is possible to segregate these hidden signals into the constituent signals. This process is regarded as deconvolution, and these independent peaks, they provide better information about the chemical structure of a molecule. Okay. Now the various tools that can be used include ANN, RF, KNN, SVM, PLS, MCR, SIMCA, and LDA. Okay. Now, where this can be used? This can be used in microbiology, in forensic science, in medical diagnosis, in foodomics, and pharmaceutics. Okay. Now, when we talk about this spectroscopic technique, I already told you that there are two types of spectroscopic techniques. So, what happens is that first one is the transmission spectroscopy, where you have the lamp, then you have the monochromator, which will change the polychromatic light into a monochromatic light. So I hope all of you know what is a monochromator. Okay, then that monochromatic light, it passes through the sample and then it enters into the detector. So what happens? The transmitted light is being detected by this detector, which is amplified, and you just record the signals. Now what happens in a spectroscopy? What we have basically, in the x-axis we are having wavelength which changes as we go from left to right, and in the y-axis we are having either absorption or percent transmittance, depending upon in what mode you want to record the signals, and you will be getting some signals like this. So this is also a signal. When we talked about a signal, what we discussed that there would be some dependent variable which will be changing over an independent variable. In most cases, the independent variable is the time, and we get, if it is a temperature, if we are measuring temperature, then we get the variation in the temperature. Okay. If we want to get the air velocity, then it would be air velocity versus the time. In this case, what is happening? Absorption or percent transmittance with respect to the wavelength. So it is again a signal. Now, the other mode of analysis is the reflective transmission, reflective spectroscopy. Now, Abhigo, to wash your face, almost sleeping. If you want to wash your face, you can go and wash your face. आप भी सो रहे थे, आप क्या ये मैंने नहीं देखा. So yeah. So next is reflective spectroscopy. Similar thing. You have the light source. You have this light source. They are being made incident onto the sample, and from there, the light beings, they are being reflected within the sensor. And if you see, the samples and the detectors, they are on the same side. They are not on the opposite side. Okay. So then you take the signal and then process it in a processor to get the spectroscopic signal. So over here we basically measure the percent reflectance. Here it is absorbance, here it is reflectance. Okay. In spectroscopy, there is a very commonly used equation. What is that equation? Basically, it is most commonly used in UV visible spectroscopy. Hmm? Now, what is that? What is that equation name? What is the name of the equation? This is called Beers-Lambert's law, where capital A is equal to epsilon BC, where epsilon is the molar absorptivity, B is the path length, and C is the concentration. Okay. Now in chemometric analysis, what happens? So just to discuss, we have already discussed. Now let's see what is the exact analysis or exact definition. Chemometrics, it combines the power of advanced statistical techniques and machine learning algorithm to tackle the complex challenges inherent in spectroscopic analysis, such as optical spectroscopy, chromatography, mass spectrometry, etc. Okay, so you can see we are applying advanced statistical techniques, including the machine learning models, to get some information from the spectroscopic data. So this is one of the uh, classical example to show the chemometric array. Over here you are having the Raman probe. You can have any other spectroscopic probe over here. The chemical is being analyzed, and then we can measure the peaks. Apart from that, we can apply the chemometrics to get advanced information from there. Okay. So what are the roles of chemometric analysis in biomedical industry? First one, medical diagnostics. It can be used in diagnosis of various diseases. It can be used in drug discovery. It can be used for biomarker discovery. And lastly, for the therapeutic monitorings. Okay. PCA and ICA, these are the these tools, principal component analysis and independent component analysis. Pardon? It is in the chemometrics only. These are advanced statistical techniques. Okay. So quite often it is also used in machine learning models also. What happens when you are getting, suppose you are getting the spectroscopic data. So if your spectrometer, it is having 1 nanometer resolution. So what you will be having? Say you start with 400 and go up to say 800. So you will be having data absorption at 400, 401, 402, 403. So you are having so much of data, almost around 800 data points for one sample. Okay, then you have to take multiple readings, and for artificial intelligence you need for two class system you need at least 200 data points, 100 from the test and 100 for the uh, 100 for the control and 100 for the test. Okay, so what happens, as per the recommended methods for applying AI into the biological data, you should have at least 200 data points, 100 in each class. Okay, for a two class system. If you go for a three class system, then you need at least 300 data points, 100 in each class. Okay, are you getting my point? So if you see, you are getting a lot of data. Now, will all the data contain the specific information? No. So now what we are doing here, so initially one of our my student, he developed one colorimeter device where the device is capable of recording the color parameters of any objects that you put it into the device. Okay, so how it is important for our biomedical applications? This is because when we talk about drug release systems or any other system, say for example, if you see those who are from the pharmacy background, they would be able to correlate. If you see, if you are having ferric chloride, then it will be somewhat yellowish in color. Okay. Now, if you keep it outside, what happens? It gets oxidized and it turns into dark color reagent. Now, what is this happening? Ferric chloride, it is being chemically oxidized and it is forming ferrous chloride, right? Now, when this is happening, that means there is a degradation of the compound, right? So, say for example, when you go to buy vegetables, what do you see? If you want to go and buy a tomato, then you will be looking into the redness of the tomato, right? How red it is. If there are any black spots, will you buy those? You will not buy those. Okay, so what you are basically doing? You are basically comparing the color information. Okay, and these color information, they can give you a lot of information about the, say, drug in the drug delivery system, about the stability of the systems. Okay, now there are ointments. How they are being made? Have you seen butter at home? If you heat it, it becomes transparent liquid. Okay, and then when you cool it, it becomes solid like structure. If you add some oil, it will become a paste like structure. What is an ointment? Ointment is also having similar kind of texture. Okay, the paste like consistency. Now, what is happening from transparent liquid to a paste like consistency, and that too there is an opaqueness. So what is happening basically? Something is going on, and what is that something? There are basically the solid fats within the system, and those solid fats, they are getting crystallized as you are cooling down the system. So when you are heating these fats, they are melting at higher temperature, and when you are cooling down, they are getting crystallized. Now when they are being crystallized, if you cool it at a higher rate, then the properties of the ointment would be different. If you cool it slower, the properties would be different. Okay. Now, as you are changing the process parameters, what is happening? Your sample texture or the formulation texture, it is being changed. Now, since that are being changed, what does that indicate? अंदर तो कुछ लोचा है, right? Say for example, some fats, as you are drastically cooling down, what is happening? They are forming bigger crystals. Okay, they might be forming bigger crystals, and they may and those bigger crystals will be full of defects. Okay, now since bigger crystals are being formed, so what is the problem? It may entrap some of your drug molecules. Okay, if you are slowly cooling, the network structure may be formed. Okay, so it will be having a different type of property. Now, if you are measuring this color profile during the crystallization process, it is possible to analyze or predict what kind of drug release pattern you may expect, because it has been found that if you change the crystallization process parameters, then there would be a change in the fat crystal network structure and properties And due to the change in the properties of the fat crystal network that is being formed in the ointments and the oleogels, the drug release properties may be changed. Now, this allows or this can allow you to predict whether there would be any change in the drug release properties or not just by monitoring the color parameters during the crystallization process. Okay. Now these oleogels, if you see, depending upon when they are being in what way they are being produced, they may alter the drug's bioavailability, it may alter the release profile, it may also alter the stability of the drug molecules. Okay. So this is how it can be related to the biomedical engineering process. Okay. Now, what are the aspects? As I already told you, drug release rate, okay, drug stability, control release, and the encapsulation efficiency. They might be analyzed if we try to monitor the color parameters during the crystallization process. So, hence, we tried to develop a low-cost crystallization monitoring system which would be giving you rapid and accurate measurement of the crystallization process in a non-contact and non-destructive manner. So next I will be talking about this monitoring process. Okay, so he has published this paper in this Journal of Food Engineering. So what happens? You have this uh, device. So what you have this Raspberry Pi, which is basically you can say a small card-like computer. Okay, so you have all of you have this ATM cards or the credit cards. These Raspberry Pi, they are slightly bigger than those these credit cards and ATM cards, and they come with a very powerful this processors. Okay, they come with very powerful processors, and they are basically regarded as single chip computers. Okay, so all the functions what you do in a computer or in a laptop, they can be done using the Raspberry Pi. Now with this, if you want to measure color, we need to have a camera. Okay, and if you want to image something, you need a light source. And since we are dealing with the crystallization process where there would be a change in the temperature of the samples, so we will need a temperature sensor system. Okay, so in this case the student has used DS18B 20, this temperature probe, which generally contains PT100 resistive this temperature sensor along with a digitizer. Okay, I hope all of you know what is a PT100. You are from mechanical background, na? Anyone who knows instrumentation engineer? PT100, what is PT100? Have you heard of thermistors? What type of thermistors there we use in industry? So what is this? So this is PT is platinum. What does 100 means? 100 means 100 ohm platinum resistance. Yeah, thermistor. Okay. So PT100 is a 100 ohm platinum resistor which is used as a thermistor in industrial processes. Okay. So this is the schematic diagram of the prototype, and this is the actual device. So if you see, there is a sample tray over here, and herein you are having the sample. Okay. So you put the sample, and then there will be software through which will guide you for the measurement process. Now the software for the colorimetric device. So there will be some front end processes, some back end processes. So I'm not going into the details of this one. So this is for the process monitoring. The device has been designed to uh, test samples with uh, just like you bring in any number of samples and you analyze the sample one by one. So that we called it called as the quality testing mode. Okay. In the second mode, we developed the program so that we can monitor any process. Okay. So this is the software panel. The as you switch on the device, you will be having this panel which will be displayed, and in this panel you will be having this control panel first. So when you talk about any device, before it is being started, it has to be calibrated, and for the imaging sensors, you have to calibrate the imaging sensors using black and white this standard black and white colors. Okay. Then, as I told you, the device can be operated in the quality testing mode or the process monitoring mode. And if you study in the quality testing mode, this test panel will be open. So over here, you enter the sample name, then click OK, and then once you do the measurement, you get the perceived color over here. Okay, then all the color parameters, they will be displayed over here. In the process monitoring mode, after you enter the sample name, you have to give the process monitoring conditions, like uh, process monitoring time, how much you want to monitor, at what time interval you want to monitor, and since we want to measure as a function of time, so at function of temperature, at what temperature you want the process to start. So that would be given over here. Okay, and then rest of the things, they are similar. And again, here there is an additional functionality where you have these color parameters like hue will be plotted over time, or intensity will be plotted over time, or saturation would be plotted over time. So in the default mode, intensity versus the time would be plotted. Okay. Now in the methodology, what you have, we do the colorimetric analysis. In this analysis, what we have done, we have uh, used 7 placards of known color parameters, and we have analyzed it with the 7 placards which were also analyzed with the standard available spectrophotometer that is available in the market. Okay. In the dilation kinetics, uh, what has been done is that it has been done in the process monitoring thing. So the samples have been heated at 90 degrees centigrade and at 3 different incubation temperatures, 5 degree, 15 degree and 25 degree centigrades, they have been monitored. Okay. Then crystallization process monitoring thing. So basically we have done this dilation kinetics only. However, the results that we obtained, they have been correlated with the differential scanning calorimeter, which is again a thermal analyzer for the analysis of the results, and so that we can correlate the results that we obtain from the developed device and the DSC instrument, which is the standard method of doing the analysis, thermal analysis of any sample. Then lastly, we took butter sample for real-time testing. So, we wanted to see, okay, under the controlled environment, it has performed well. So whether it can also perform well on other fat-based formulations or not. Okay. So if you see over here, what happens? We are having these black and white placards which have been used to calibrate the this sensor. Then by getting into this quality testing this thing, so they see the color placard, it was inserted and then the reading was taken. So this is the perceived color, which is basically the synthesized color. Now if you compare this color over here, they appear to be similar. Okay. So but the thing is that what we have done, we have automated it, and here we are getting certain numbers. When we go for buying the vegetables, we are perceiving the same thing without having these numbers. Okay. So Your perception will differ than mine, mine perception will be differing from yours, and so on. So everyone's perception, it will change. So when you go to the industry, such kind of change in perception, it is not acceptable, because if we change the, say, testing engineer, and if the perception changes, okay, so what will happen? There might be a variation in the production batch. Okay, there might be a variation in the production batch, and if there is a variation in the production batch, so what will happen? The product may not perform as well as we should be expecting. Okay, so again, what we did is that we developed these placards using some standard color parameters. Then we took the printout, and these are the color uh, details that have been acquired from the commercial device, and lastly the color details that have been acquired from the developed device over here. So that we have taken, and then we have calculated delta E. What is delta E? Delta E is nothing but the comparison between the original placard color, and if I am looking into the commercial device results of L star, A star, B star, so those color parameters, comparison of that one with that of the uh, actual color parameters. Okay, and if you see the color parameters over here, the delta E of our developed device, it was quite low. Okay, so it is a matrix to analyze whether there are any perceivable change or not. Okay, so here the samples were analyzed, and as I told you, we can get the time versus the intensity plot, and also the results along with the temperature and the color parameters, they would be saved in an Excel sheet. So these are the normal colorimetric analysis which have been done after at the end of the study. So gelation kinetics, if you see, the gelation kinetics are there. So we are getting this, if you see, temperature versus time graph that we already discussed previously, that the temperature would also be saved. So from here we can get information about at what time the crystallization starts. So the initial phase, it would be the nucleation phase. After the nucleation phase, the crystallization starts, and then we get to the point where we have reached to an equilibrium stage. Okay. So from the graph, we can tabulate these things, and then by using the exponential decay model, if you see, it seems that all these graphs, they are exponentially decaying. So using this formula, using and calculating this k, we can find out the crystallization rate. Okay, and once you find out this crystallization rate, we will be able to get the rate of crystallization of each and every sample. So if you see, just by analyzing the color parameters and the temperature profiles, it is possible to find out how the crystallization or the gelling kinetics, it is taking place. Okay, so again, if you see, these are all signals. We have measured the color parameters and the temperature profiling with respect to time. With respect to time. Now coming to the crystallization process monitoring. In the crystallization process monitoring, we have changed it to temperature because data is already with us. We have changed the independent variable, and with respect to the independent variable, we looked into the L star value. We looked into the other angles also, but we found that L star value, it was giving us a proper correlation with the thermograms. That's why we have plotted this temperature values. So if you see, initially this is the nucleation phase for each of the sample, and then after the box 1, which is basically the primary crystallization process, so we got the primary crystallization process, and after the box 2, the secondary crystallization process, it has started. And this is at 5 degree centigrade in the incubation time, this is at 15 degree, and this is at 25 degree incubation time. So it has been shown over here. So again from there we got those values and we have tabulated those. These are not important for you to remember all these values and all these things. Just I am trying to make you understand uh, that how you can design and develop some small things which may be useful on a broader sense, because as per the institute policy and as per the NEP, as I already told you that I have to include around 20% of the lectures based on design and this thing related to biomedical signal processing. So that's why I am including all these things. Okay. Now, if you look, then we did the biomedical this butter sample analysis. In the butter sample analysis, this is the nucleation stage. Then we had this block 1, block 2 over here. Over here, if you see that there was a dip in the absorption reflectance spectra. Okay. Now, thereafter, we get to another process where we are having another transition. Now, if you look over here, as we go from 50 to 10, so this box 1 is at a similar temperature as that of this peak 1, which have been obtained from the DSC. Okay, and this from this box 2 we have another peak sample over here, a peak in the DSC. Okay, so we can see that the device that we have developed, by measuring these color parameters, we are able to efficiently monitor the changes in the sample during the preparation stage. Okay, so if we can do that, it will be easier for us to monitor the thing. Okay, any question till now? Okay, so I'm not going into this one. So development of ML enabled spectrometer come colorimeter. So what we did is that when you try to include some this ML models into the system, what happens is that the single chip computers, they might not be quite useful, and also we have to get some spectroscopic data. Okay, so in those cases, in from only the RGB scale. Okay, so what happens when you are having this visible spectra, which is say from 380 nanometers to 780 nanometers, your R is over here, red component is somewhere here, this is B, and G is somewhere around 680 or something like that, or 550, around 550. Green component is there. So we are basically talking about only three wavelengths. Okay, we are basically talking about only three wavelengths. But in a spectrometer, what you have? We talk about multiple wavelengths. Okay, not only RGB, but we talk about this information about multiple wavelengths. Okay, now when we are doing this, so we are only getting the RGB from the camera. So what to do it? What to do basically, right? Now we have to take this thing and we have to find out the transfer function T, which will allow us to generate the spectrogram. Okay, say for example, if we say that the spectrogram data, it is this one. Okay, so our transfer function, it would be it would look something like that. That means to get the spectroscopic data, we have to apply some transfer function on the RGB data to get the spectroscopic reading. Okay, now you are having a lot of data point. Now this computation, it will take a lot of resource which may not be possible in the single chip computers. Hence, what we did, we got rid of the Raspberry Pi. In short, we call it as RPi. We got rid of the RPi and we used USB connectors to connect it to the computer. So background, why we are interested over here. This is because around 600 million people they fall ill, and uh, 4,20,000 die annually due to the foodborne diseases. Okay. Now this results in the surge in the hospitalization and ultimately leads to the potential delay in the healthcare. Okay. So detecting the food spoilage, it becomes an important and essential criteria. Okay. And this also helps us in preventing gastrointestinal diseases, infections, and even chronic conditions. Okay. So apart from this, it also helps us in global food security. Spoilage detection uh, is where spoilage detection is key to reducing the food waste. Okay. So this is because if you can detect that the food is going to be spoiled at an early stage, you can consume the food quickly before it gets rotten. Okay. So in our household, if you see, if something is being stayed in the or kept in the fridge for some period of time, our mother will say you finish it off early, so then after you can open the new food products. Why that is so? Because they are trying to save the food wastage, right? Now herein, in this graph, different modes of wastage of the foods it has been reported, and if we consume this food, we can have food poisoning, and it leads to the surge in the hospitalization. So in this way, you can say that developing small devices can also help us in reducing the thing, in reducing the this burden on the hospital to a great extent. So what he has done, there is nothing. There is basically a camera and a light. So all of your mobiles they are having. So if you can develop an app, a simple app that will that can help the people in understanding whether the food is getting spoiled or not. Okay, so that can be done. Okay, so this is an easy way to implement something. So likewise, you can think of other things also which can help in the field of medicine. Okay. So this is the hardware developed. As I told you, it is just related with this is connected with the computer or the laptop. So this is the flow diagram. I am not going into the details. So what he did is that we took a bread sample, then we took the samples in the bread containers, and herein you are having this filter papers, Wattman paper. I think 40 has been kept, and in the control sample we don't have any nothing. Okay. Now on after keeping the samples on these filter papers, 1 microliter, in this one 10 microliter, and in this one 100 microliter of clove oil have been put. Okay. So control S1 is this one, S1, S2, S3. Okay. So these have been kept. Why we kept clove oil? Clove oil is a known antimicrobial agent. I didn't get you. Okay, we will come in at a later stage. Let me finish this off, then we will discuss. So, I hope by the end of this experiment, you will be able to get that information. So, what we did the calorimetric analysis, then spectral analysis was done. Then we did the microbial study to find out what is the actual spoilage data, microbial data, so that we can correlate with the microbial spoilage information. Then we did the ML modeling. ML modeling was done using this colorimetric and spectral data. Okay, so we took that and then we developed the models. So ML modeling, so data was collected, data was pre-processed, then we chose the ML and training models. Okay, so there should be a space over here. Then evaluating the models was done, then predictions were made. So ML based classification, it can be of two types. Khalid sir is teaching you AI ML, right? So over there you must be knowing by this time that the ML models can either be supervised learning model or ensemble learning models. So we used both of them and we selected three models from each of them. There are hundreds of models, but you have to put some restrictions somewhere. Okay, so we used these models uh, and then out of that we found out the best model which is suitable for our analysis, and that was being uh, deployed or employed for early detection of the spoilage. So data pre-processing, we have this data collection. So over there we got 12 color parameters and 36 spectral parameters. So in total there were 48 features. So these two datas, they were integrated. So that is called data integration. Okay. So these steps you should remember what I am telling. Just like over here, if I ask you, how do you develop a model? So first, what are the steps in ML modeling? So you have to discuss about these things. Okay. You don't have to remember all the experimental results, but what are generalized things that you should remember. Okay. So there is this data integration. Okay, from where we combine this color and the spectral information. Then after that we need to reduce the feature set, which is called dimension reduction. So the dimension reduction is being done by feature selection method. In the feature selection method we used forward selection method. Okay, there is also backward selection method. In the forward selection method, what happens, you start with a smaller number of features and then you go on increasing the number of features. Okay, so herein we started with 5, then did 7, feature number 7, 10, 15, 20, 25. We increased it up to 25. Okay, the models that were being used, these are this. So RF model, SVM model, decision tree, then Agabus model, GBT and extreme GBT. Okay, so from here we found that when XGB was used, extreme gradient boosted tree was used, it gave the best performance with the 15 features. So it was the best performance. With this combination, we got the best yield. And how it did, it has been reported over here. Start with this one features and then keep on adding the features. So it will try to find out. And when you get the thing, it will stop over here. If there are no improvement. Uh-huh. Pardon? So it's all, see, uh, when you do this machine learning, we do not interfere. Okay, if you are interfering with the learning method, then what happens is that you are including a biasness. You are including a biasness. So you allow the algorithm to choose for yourself. Okay, so we are not interfering. So it starts with the single feature and then we keep on adding the thing. So we started with 5, then we took randomly 7. ये जो 5 भी जो है, that is not selected by us. So it will, out of these 48 features, it will first take a set of 5, then it will do permutation combination, it will then select another 5, then it will do another permutation combination, then again it will select another 5. So it will perform all these permutations and combinations, and from there it will find what is the best result in 5. Similarly, then again it will move forward, then you will be having this 7 features that will be incorporated. Okay, then again it will increase the features, it will go to 8, it will go to 9, that way. So ultimately, after doing all these, running all these programs, it came up with the 15 features when the XGB was used. So we are not interfering. It is the machine which are telling us that these are the 15 features which gave us the best result. Exactly. It will do all the permutations and combinations. Okay. So from there, if you see, a new data set was created, which is having a lower number of data points as compared to the original data set, which was having 48 things. So herein we had 6 color parameters and 9 spectral parameters. So model training and testing. So when you have this new data set, from here you have this training set, which is the control sample. So training and validation of the model was done using the control data set, which was not having any clubber. Okay. So again over here, if you see model hypertuning and training, we are not doing, we are not interfering with the data set. The system will automatically do, and over there we are telling the system you adjust the hyperparameters of RF, SBM, TT and all these algorithms. And how do? You apply the grid search CV algorithm to do the parameter search, and from there it will come up with models with best parameters. Now from here you get to the model validation. वही कंट्रोल सैंपल में यूजुअली व्हाट वी डू, आइदर वी गो फॉर 60-40, okay, or we go for 70-30. What is this 60-70? These are the training set, and validation it is being done on the 40-30. Here for the testing of the samples, what we have, we used the samples S1, S2 and S3 as the test samples. Okay, so over here again we went for the training and validation of this one. Okay, so this is basically the deployment, right? After testing we have the deployment. So by now you must have understood what we are doing. We are taking the color and spectral parameters which is associated with the functional groups or the chemical groups that are present in the sample, and then we are applying the machine learning models. Okay, then we are applying the machine learning models. And what are the different models you can apply? You can apply both classification and discrimination methods, or you can apply the regression and the prediction method, whatever you want. Okay, so result spectral analysis, if you see what we got from our device, the from our device and the standard device, they are pretty similar. Okay, and this is how you get a spectral thing in the spectrometer. Okay, so when you do the color analysis, if you look into these parameters, any of the color parameters, if you see only on the 10th day you are able to segregate the samples. Okay, in comparison control from the parameters, and over here we could not segregate. Okay, because there have been overlapping of the data sets. So color parameter itself, they are not as much useful for predicting the spoilage. Okay, and that too it is being able to detect the spoilage at the 10th day. So what we did, we also took the spectral parameters. So in the spectral parameters, if you see, as the days are progressing, there is a reduction in the this spectral intensity. Okay, now as he was telling, when it is getting spoiled, how do you know? We know by performing the total viable count analysis. Okay, so what is total viable count? How many bacterial cells are there within a specific grams of sample, and viable cells, and that's why we call it as CFU, colony forming units, colony forming units per gram of the sample. Okay, so you do this And as per the literature, if the TVC is less than 10 to the power of 5 CFU per gram, then the bakery products, they are regarded to be safe for consumption. However, if it exceeds this value, then we call it as a spoiled. So you have to experimentally do it at the initial stage to define your limits. Okay. So herein, what we have done, if you see, we have taken 8 into 10 to the power 4 as the fresh class in the range between 8 into 10 to the power 4 to 1 into 10 to the power 5 as the early spoiled. That means under this condition, you can consume the product without having any detrimental effect on the heart on the health, right? And then the last one, where the TVC reading, it goes above 1 into 10 to the power 5, so you call that as the spoiled. And herein how you get the readings, plate readings. Pardon? Yeah, definitely. When you talk about any food products, it comes with some storage restrictions. So it is expected that you are following the storage restrictions. And usually what happens is that even if the expiry is gone, if you buy any product, अरे पैसा ये खरीदे अभी तो दिख नहीं रहा है कुछ, so let's have the food. We always try to save the money. If you see our parents, they would be more concerned about this, right? अरे अभी तो खराब नहीं है, चलो खा लो. अरे रोटी खराब नहीं हुआ है, ठीक है, बच्चों को नहीं देना, हम तो खा सकते हैं, right? So this goes on, right? So but the thing is that when you're talking about this expiry also, what the company do is that if they experimentally see that the bread is getting spoiled at say after 8 days, if you look over here in the control sample, we got that the early spoil, like, it starts at day 8. However, if you try to buy a bread, you will find that it will be having an expiry date of say 3 days or 4 days, something like that. 2 days, 3 days or 4 days maximum. Now, companies give you a buffer days of say up to 8 days, double the time. Why they are doing it? If they keep a smaller time frame, and by chance the product gets spoiled at an early stage, suppose they keep it at say 10 days or 8 days, तो मान लीजिए आपने उसको ढंग से नहीं रखा, it gets spoiled say within 6 days, then you will be putting a claim onto the company. So they don't want to go into those legal battles. So they will keep a shortage ये time frame. तभी तो मम्मी लोग और पेरेंट्स लोग जब खाते हैं बासी रोटी या फिर this पुराना bread, they don't get ये adverse health effects. Why? Because the microbial count is low, right? So this is it. So if you see over here in the control sample, we got at day 8 early spoiled, and at day 10 the sample got spoiled as per the microbial study. In S1, S2, S3, in day 8 and day 10 early spoiled. In S2, S3, only the day 10 were early spoiled. They were not spoiled. Okay, as per the microbial count. Then we got those 15 features. We applied those things. यहाँ पे देखो RF F1 score 90.68% accuracy, XGB 92.44 accuracy. Okay, so we got two models which is giving us an accuracy of 90% or above. Okay, and see, we are not doing anything. All the things, whatever the predictions we are doing, it is being done by the machine learning algorithms only, right? So these are the parameters you will be studying in this thing, AIML class, right? We have selected, no? That's why we have given green. We have highlighted this too. Oh, in GPT. Uh, in it was because, yeah, see, if you look into the average, so it is having the highest and the second highest you have just taken. If you want to take more, you can definitely take it. But as you, as there is a decrease in the what you call, um, decrease in the F1 score or the accuracy level, usually we don't, we just consider the best one and at the max the second best one. We don't go for the third one. No, if you see, it is 88%. This is one is 88%. This is 75%. So they are not giving us best result. And another important thing, this GPT and XGB, XGB is extreme gradient boosting tree. So this is an advanced version of GPT. So that was another reason for not selecting that. एग्जीक्यूशन टाइम मीन्स वो कितना टाइम ले रहा है उसका प्रेडिक्शन के लिए वो जो मॉडल जो ट्रेन होता है हाउ मच टाइम इट टेक्स फॉर द ट्रेनिंग हाउ मच टाइम इट टेक्स फॉर द वैलिडेशन so combining those two you get the execution time how long it took for a model to get trained and then validated that is the thing so jitna usually आपका execution time it is higher the more is the computational burden okay. So from here, these are these error curves. So this training and the validation errors, they are not crossing over each other. So you can say there was no uh, overfitting of the data, right? So you will be studying it in the AIML class. So this is the ROC curve. I'm not going into the detail. Now coming to this thing, this is the table which we discussed at a previous year. Same चीज देखो just in a proper way so that we can correlate with this table we have. तो यहाँ पे early spoiled था यहाँ पे fresh early spoiled. Now if you look into the readings, RF, D8 and EL early spoiled. So most of the classification is early spoiled. Okay. In S2 fresh early spoiled, higher number of predictions are here. Similarly over here 80% tricky. Similarly, in XGB, 90-90, then this is fresh, early spoiled. So, if you see our results, they are quite matching with that of the microbial count. Okay. So, in this way, you will be able to correlate your machine learning data with that of your experimental data. Okay. So then again, there are certain models which you can uh, uh, implement, which can give you an approximate day of the what you call of the sample, original sample. Say whether it is a day 5 sample or day 8 sample or day 9 sample, that can also be predicted. Okay. So suppose you go to a restaurant and you find out that there are chicken pieces which are lying. So what is the day of storage of that of those chicken or the mutton pieces? How do you find out? There are various ways, chemical ways they are there, but they will be time consuming. So if you want to predict something, then you can develop this kind of strategy wherein you can rightly predict from there that this is the day of this sample or the what do you call the storage day of the sample or the this sample has been stored for this many days. Okay, after it has been harvested or taken from the butcher house. Okay, so that's it.